Okay, so welcome back to linear algebra class. Um, okay, thanks for your patience while I try and figure out some new technology. Yeah, so what I want to do first is just post a quick review of kind of where we were before spring break, and then hopefully we can kind of jump back into things later on this week. Um, okay, so to that end, I want to look at linear algebra review, and I can also upload these notes once I'm done with this. So, okay, where we were is we were talking about systems of equations, and we could have something that looked like this. So 3x1 plus 2x2 equals 1 minus x1 plus x2 equals 3. And then x1 minus 3x2 equals minus 7. And we started day one kind of talking about how to solve things like this. But we've also seen that this is the same as the vector equation that looks like this. So I can write the kind of coefficients paired with x1 as a vector, which I can multiply by x1. And then I can add that to the coefficients multiplied by x2. Can keep that in another vector, and then I can set it equal to what we had on the right-hand side. So this vector 1, 3 minus 7. And but we also saw that this is the same as the matrix equation where I have this sort of coefficient matrix, 3 minus 1, 1, 2, 1 minus 3. And that's multiplied by the vector containing x1 and x2. And then that's all equal to this vector 1, 3 minus 7. And I can kind of think of this as my vector, or my matrix A. This is the vector x, and this is the vector b. So here I can think of this as sort of ax equals b. And we know that we solve this. Oops. All right. Solve by putting this coefficient matrix A together with B in a matrix and putting that in a reduced row echelon form and seeing what happens. And we also saw that if B is equal to the 0 vector, then this is called a homogeneous system. Oops. Okay. And if this is the case, then we know that there's always one solution, which is the trivial solution, and that's to let the x's all equal 0. So always has trivial solution. Okay. All right. Move that up. And to that end, so we can think of the columns of A. So if I write A as maybe vector A1, A2, 2 sum, AP, I can think of those as vectors. So AIs or the columns. our vectors. And I'm interested in when this matrix equation, AX equals 0, doesn't just have the trivial solution. So when does AX equals 0 not just have the trivial solution? Okay. And to that end, we have this definition of linear independence. So we'll say that a set of vectors, maybe v1 through vp, is linearly independent if this equation C1 V1 CP VP equals 0, where the C's are all constants and the VI's are vectors. So a set of vectors is linearly independent if this has only the trivial solution. Meaning that the C's are 0, and that's the only solution. And we say that the vectors are linearly dependent if the above equation has infinitely many solutions. So remember, with a system of equations, we said that there are 3 possibilities, either one solution, no solutions, or infinitely many solutions. But with something like this, we know that it always has the trivial solution. And so then it either has one solution, the trivial one, or it has infinitely many. And so if it has one, then they're linearly independent. And if it has infinitely many, then they're linearly dependent. Okay. But given some set of vectors, how do we determine whether or not they're linearly independent or linearly dependent? And we said that we can do that. So determine linear independence or dependence by putting the matrix, putting the matrix with the vectors as the columns, v2 up to vp, and the last column being the 0 vector in reduced row echelon form, and looking for free variables. And so if we solve this and there are no free variables, then we said that that implies there's only one solution, and it's unique. So that implies that these vectors are linearly independent. And then we said that if there are free variables, then that implies that they are linearly dependent. Okay, and we made a couple observations as well about being linearly dependent. So if this is the case, then that implies a couple of things. The first is then that at least one of the vectors is a linear combination of the others. And we proved this in class, I think, on our last day of class, the Monday, the review day. But what this means too, remember, if a vector is a linear combination of the collection of some other vectors, then it's in their span. So we'll say at least one vector is in the span of the others. Okay. All right. And lastly, a couple other observations just about vectors in Rn and what we can tell automatically just by looking at the number of vectors that we have. So if we're in Rn, we can make the following observations. So first, a collection of p vectors with p less than n cannot span. So I think you showed this on your homework, where if you had a collection of 3 vectors, you couldn't span R4. And then we talked about in class how that's not just true for 3 and 4. In fact, it's always true with some number p that's less than n. But we did talk about how if you want to span R4, then you need 4 vectors. Same if you want to span Rn, you need n vectors. And so if you have more than that, it turns out to be too many. So a collection of q vectors with q greater than n is going to be linearly dependent. And I'll leave that for you to prove if you want on your own. Okay, however, so if something smaller than n is not enough, and if something larger than n is too much, then the question is, well, if I have exactly n vectors, is that going to span Rn? And the answer is not necessarily. So we'll say that a collection of n vectors may or may not span Rn. And it turns out that the n vectors need to be linearly independent in order to span Rn. To span Rn. Okay. All right. And so lastly, we left off talking about linear transformations. So linear transformations. All right. Linear transformations. Okay. Here we first defined what a transformation is. So we said a transformation T, which goes from, let's say, Rn to Rm, is a rule that assigns to each vector x in Rn. So notice here this word each, that means I can plug in any vector I want. Similarly, if I have just a normal function. The input that I can use is all x values. So it's a rule that assigns to each vector x in Rn a new vector, not necessarily new, but a vector t of x that's in Rm. And we call this the image of x. And so we said here, here is Rn, and here's my vector x. And then over here, I have Rm, and my function just takes x, this is t, sorry, my transformation takes x and sends it over here to some new vector, t of x. Okay, and we are going to be, so we talked about last time how, so I'll say recall, when I have the transformation t of x equals a of x for matrix A, this is what's called a matrix transformation, is a matrix. And these are the type of transformations that we're going to be interested in. And okay, so we have a transformation. I said we're going to be interested in a matrix transformation, but the last type of transformation that we talked about is a linear transformation. And so we said that a transformation, sorry, getting used to new technology. Okay, so a transformation T is linear if the following two things are true. So first, if I have a transformation of a vector u plus a vector v, that's equal to the transformation of u plus the transformation of v. And here, u and v are both in Rn, so they're input vectors. And also, if I have the transformation of C, where C is some constant times a vector u, then that's equal to C times the transformation of u. And here, C is in R, it's some real number, and u is in Rn. And if a transformation fails even just one of these, then we say it's not linear. So if it fails both, it's not linear, but also if it fails just one. So maybe we'll put that. So failing one or more of these means the transformation is not linear. Not linear. Okay. All right. And okay. Lastly, one observation. So notice because we can put in any x, observation, if t, the transformation is equal to this matrix transformation that we said we were interested in, then the range, kind of what's hit up here, is really just the span of the set of all linear combinations of the columns of A. And it will turn out, so this is where we'll pick up later this week, probably on Wednesday, the following theorem. So a transformation T from Rn to Rm is linear if and only if there exists a unique M by N matrix A such that T of X is equal to A times X. So what this is saying is that if a transformation is linear, then it will actually be one of these matrix transformations like we've been talking about. So given some transformation, we'll be able to find this matrix A that is associated with it. Okay, so that's the review, and let me see if I can figure out how to stop.